Okay, we're live from Studio City in Odessa, Texas. Wait, Studio City's not in Odessa, Texas. My brother lives in Studio City. That's pretty darn near LA. It's like all one big city, right? You got Pasadena, Studio City, LA, blah, blah, blah. It's all right there. Yeah, Burbank. Yeah. Okay, this is where we were. So if y'all want to chat, I'm all for it, and you can go outside and just chat away. You know, it's all cool. You know, it's very good to release and talk to one another and discuss problems and issues and boyfriends and girlfriends and boyfriends and girlfriends and however all works out for you. I don't know, but yeah, I love that. That's always a lot of fun. Um, what happened this morning and yesterday and last week, and man, you should have been at this party, or you should have been at my house because it was a party over the weekend. Oh yeah, uh-huh, 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 but you don't have my address. You're not getting it either. Okay. So anyway, we're talking about energy, how cells make that, which is fun, which is, of course, they have to make their energy in order to stay alive. So this becomes critical to stay alive, very critical, which is how you stay alive, because you got all these cells, and they all have to stay alive, so they're all basically doing the same thing in order to stay alive. So in order for you to be alive, then all your cells have to stay alive. And so, you're just an aggregate of 70 trillion cells. We got to know, if we know how one works, we basically know how they all work. And so that's what we've been doing really all along, and looking at the cell. So that's really where we are. We've progressed to the cell. I know you don't think that's far, but that's really quite a bit of distance in biology. So we need to talk about energy a little bit. Kinetic energy is energy of motion, and if you run real hard and smash your head against that wall over there, I don't know, but that's a sheetrock wall. I don't think you'll do a whole lot of damage to your head. You probably might put a hole in that sheetrock. Probably wouldn't be too hard to do that. Anyway, kinetic energy, you expend the energy once you slam into that wall, but you do have energy in motion itself. There is energy in that. So, and we'll see that in a cell also. Cells have the ability to move something from point A to point B, and in the process of moving it, there's energy that is created, which is pretty cool. Mechanism in order to produce energy. They move things from here to there, and energy comes out of that process. Potential energy is energy because of its position. If you have a boulder at the top of a hill, it has potential energy. If you give it a little bit of a shove and push it down that hill, it goes rolling down the hill, and eventually it will stop at some point, running into something and expending the kinetic energy, because it begins to roll, so it goes from potential energy to kinetic energy. So for us, our potential energy that we run on is food, obviously. That's what we put in our bodies, and that is our potential energy. And what we do with a good deal of it is we convert it to sugar. So we run on sugar. And although most consume a lot of sugar, I'm not a really big sugar fan. There's only one sugar product that I cannot stay away from, and that is a fresh, warm chocolate donut from Southern Made. I will sit and eat 5 of those things until they're coming out my nose. Seriously, I will just cram them in as fast as I can. But other than that, I'll have a big old bucket of ice cream in my freezer for months and months, in case you can go, oh, there's ice cream in there. Never even dawned on me that I have ice cream. I don't even think about it. I see it and I go, well, maybe I'll have a little ice cream. No, wait. 4 months later, it's like, oh, look, I've got ice cream. I forgot again. But sugar's not my thing. I like fat. Fat is good. Fatty foods. Fat. But a whole bunch of what we consume is not going to be sugar. It's going to be protein. I really like a lot of protein. I like a lot of fat. So I like meats that are very, very fatty and have lots of flavor, like a ribeye. Those are excellent. But you take a whole bunch of that. If I eat too much, say, protein, too much of a ribeye, then a lot of that's going to be converted into sugar because I don't need that much protein. You know, I'm not in a growing period. This is not a growth period for me. I'm in the dying phase. Yes, it's true. It could happen at any moment. And I'm very, very comfortable with that. A death at any moment could just be fine. But, you know, so if someone wants to blow my head off, you know, here it is. It's right above his neck. You know, but don't hit me in the shoulder because that's really going to hurt. If you hit me right here and blow my head off, then, you know, I don't even know anything happened, really. You know? And don't say, hey, and then I'll look and see the gun. Just blow my head off, you know. I don't even want to know it's coming. You know, I want to go, you know. But if you're firing real fast, and I don't even have time to go like that, you know. It's like, no. You know, I don't know what my response would be. Like, hit me. Come on, take me out. Leave these people alone. You know, they got lives to live. I've done enough. I've done more than I ever should have. I can promise everyone that, and God knows it. He's like, you know, your number, you're right there. Your numbers are coming really close. It's all good. Okay, so anyway, those are two basic kinds of energies. There are other types of energies, but anyway, potential energy. And kinetic energy. Here's thermal energy, type of kinetic energy associated with movement of atoms or molecules. And then heat is just really, it's a measure of thermal energy being transferred. That's what really heat is. Light is a type of kinetic energy. We can use light, which plants do, in order to produce sugar. And it is energy of motion, but it's the motion of what they call photons, which are really wavelengths of light. You have different wavelengths, like from purple to, from violet. It's kind of like in a rainbow, if you've ever noticed. You go from if you're on the inside of the curve, that'd be the shortest wavelength. Then you go from violet to blue to green to orange to yellow, and then you get to red, which would be the longest wavelength. So violet is the shortest wavelength. Blue's a little bit longer. Green's a little bit longer. When you get out to red, it's pretty long out at that. So that's the sequence from short wavelength to long wavelength. But it's really the movement of those little particles of light that move on that wavelength. And the movement of those is the kinetic energy. Plants use that energy. And it's, I think, wonderful to have some understanding of how that works. Thermodynamics is a study just like biology. Bio means life. Ology is a study of, so it's a study of anything living. That's a huge topic, folks. That's humongous. Big, you know. You can study just fungus, become a mycologist if you're interested. You know, I started a PhD in mycology, actually. Just the study of fungus. I kind of thought it was cool. Anyway, didn't finish it. Don't care to finish it. But many different aspects of biology. Thermodynamics is the study of energy relationships. It is a science, a study of energy. You know, how do you think they design cars now that can get, say, like I have a hybrid automobile? Anyway, it's a Lexus actually, but it's a Lexus CT200H. CT200H. You need to look that up because those are pretty cool. Very comfortable, get an excellent gas mileage, anywhere from 42 to 52 miles per gallon, depending on how you drive it. So it gets good gas mileage, and it's kind of my automobile to go back and forth to Alpine. Um, anyway, pretty good gas mileage. Give it some time; they'll get better. And of course, eventually we'll go to electric automobiles just completely. And then as soon as they've sucked us all into buying electric automobiles, they're trying to get us all to buy hybrids now. So we will all buy hybrids eventually at some point. As soon as we all own hybrids, then they'll come out with, we've got now just so totally electric cars that can get 300 miles per gallon, 300 miles per charge or whatever. Then we'll go, okay, we've got to have one of those. So we get rid of the others, and then we buy the electrics. And as soon as we all own electrics, then they'll go, oh, wait, now we have hydrogen-powered automobiles. Look at this. Wow, man, these are cool. These are better. So then we all buy those and get rid of the electrics. Yeah, we're being played like a cheap violin. Played like a cheap violin. Sure we are. We should just all buy horses and tell them to stick it up their nose. A horse? I'm on a horse now. I ride a wagon to school. What do you think about that, Mr. GM? Anyway. And it can go pretty fast. It's got 1 horsepower. So study of energy, which is very cool. If you're into designing automobiles, and I love automobiles. I'm an automobile freak. I want a black 911 Porsche. It's just something I want. I'm not sure I'll ever be able to afford to get one, but I think if I spend enough time on 2nd Street, pedaling, then I think by the time I'm 150, I might be able to get one that's old and used and broken down and doesn't run. Yeah, dream on. Kill that fantasy. Study of energy relationships. Anyway, there are 2 laws of thermodynamics. The first law is what they call the law of energy conservation. Law of energy conservation. It actually has another name instead of just first law. Most people just know it as the first law of thermodynamics. This means that you cannot create or destroy energy. It's impossible. So if you take gasoline and you burn it in your automobile, it becomes other types of energy. It releases CO2 in the atmosphere. It releases water into the atmosphere. It releases carbon monoxide into the atmosphere, and it is released as a tremendous amount of heat. So if you've been driving your automobile for about 3 or 4 or 5 hours, driving to Austin or something, when you're finished, get out and just lay down on your hood. Just see if you take your shirt off, see what that feels like on your hood. It's going to be hot, real hot. So yeah, you give off a lot of heat on that one. So you can't really create it. The ultimate source of energy is the sun. Plants use that in order to make sugar, which then the plants grow. And then we eat the plant, and then or the animal that ate the plant. We're just transferring energy from one place to another place. And then, of course, on the gasoline and those types of hydrocarbons, we get those out of the ground. Well, those used to be living organisms that were buried over and turned to oil and gas, and now we collect it and burn it. So we don't create it. We can't destroy it. It's just transformed from one type of energy into another type of energy. That's all that ever happens. Okay. And then the second law of thermodynamics, this time is when you do an energy transformation or transformation, when you take it from gasoline, you convert it into carbon dioxide, carbon monoxide, heat, water, you make all the products from it, you burn it. You also release heat, obviously. Some of the energy is actually lost, not destroyed, because you cannot destroy energy, is lost in a non-usable form. That would be the heat, non-usable. We don't use it for anything. I don't know, the heat put off by my automobile, I'm not using it for anything. I don't do anything with it. I guess you could put a frozen pizza on top of your engine and drive from here to Austin, and then when you get out, have pizza. put it on top of your engine. There you go. Pizza time. Well, I suppose. I've heard of people doing such things. And, the heat that we give off, we've got 37 degrees Celsius, 98.6. The room is at 98.6 degrees Fahrenheit. You'd all be like sweating and hot and feel horrible. But your body temperature is 98.6 degrees Fahrenheit. So there's a lot of heat being radiated out of our body. We don't do anything with it. If you get up from your chair seat's warm. Well, it went into the chair seat. Chair seat isn't going to do anything with it. Doesn't care at all. The heat that develops in this room because of our body heat isn't doing anything with that heat. So anytime you do a transformation like from us basically converting sugar into another form of energy called ATP, because that's what we produce, energy is released in a non-usable form, which is called heat. And we're not saying heat is not usable at all. We're just saying that when you do transformations, you don't get 100% energy conservation in that you don't use all the energy that you started with. So if you start with a certain amount, 100% energy, when you're finished with it, best case scenario, you're only going to get about a 50% energy efficiency. And that would be the cell. The cell gets about a 50% energy efficiency. The most efficient, basically, machine on the planet is the cell. Nothing is more efficient than that. It doesn't happen. So that's admirable. The other thing, and this is the weird part about second law of thermodynamics, is when you go through a transformation, say that we take sugar into our body, and we go through a process where we produce energy, ATP, that we can spend, but we also make some heat. We also produce some carbon dioxide, which we exhale. We also make some water. So what we've done is we've taken, a relatively simple molecule, which is called sugar, glucose, and we've broken it into many, many pieces. We've got carbon dioxide coming out. We made some water. We made some heat. We made some ATP. We broke it into all these little pieces. And so that means we've increased the randomness. It becomes more random. So when you do transformations, whatever you start with becomes more random at the end of it. So during transformation, randomness occurs, and that's called entropy. Entropy is what really powers most businesses. Okay, so if you're in the air conditioning business, heating air conditioning, so you sell central heating air conditioning units. So occasionally you got to buy a new unit. It'll die. They die. The engine, the motor just completely wears out, so you got to buy a new one. They're pretty expensive. I hate that. I'm like, what? It doesn't work anymore? I have to buy a new one? Well, that's really pretty expensive. Let me see if I've got an extra $5,000 in my back pocket. You think? No. No. Where am I going to come up with this? Back to 2nd Street, But anyway, they're expensive. So that's how that business operates. It's like, things begin to wear out on the heating air conditioning unit, and then you have to replace them. So they stay in business. I have a refrigerator that has been running since 1945. 1945? Still running. It's been running since 1945. I bought a refrigerator not too long ago from, I don't know where I got it. I think it was Best Buy or wherever. It doesn't really matter. And the guy that delivered it, I asked him, well, how long, because this is a pretty nice refrigerator, and I asked him, I said, is this a nice refrigerator? And he said, yeah, it's probably one of the nicer ones that you can probably buy other than commercial refrigerators. And I said, so how long should I expect this one to last? He said 12 years. I have one that's been running since 1945. They make things now to wear out. They have a life of however many years. So they will wear out, so you will buy another one. It keeps them in the refrigerator business. So they have to make more. So you have to buy because they continue to wear out. You know, when they can make them to last, I don't know, 10, 20, 30, 40, 50, 60, 70, 80 years. They can make them to do that. You know, technology should be better, and they should be making them now that will run a lifetime. But they don't. They're making them so they wear out. Welcome to America, you know, land of, we're going to suck every nickel out of you that we possibly can. And you're going to have to work as hard as you can possibly work in order to buy all this stuff that you're going to want, because it's just going to continue to wear out on you. So you're just going to have to work harder. It's called America. This is where you live. And am I always happy about that? Not exactly. I don't think there's a country that I've been to that I think I might rather live in, although I consider that. Just retiring, heading to different places. There are different places I've actually looked at and I've been, and I think, well, I could probably live here, that are not America. So, you know, I am glad to be an American and to have lived in America, but I think so much of it is corrupt now that I'm not real pleased all the time. I'm not real pleased all the time. So, anyway. So, entropy. Anyway, back to that. Things become random. You buy a new automobile. How long is it new? I don't know. You know, it doesn't take it, but what? Up to 100,000 miles if it's basically an American-made automobile. You basically have to get another one by then. 100,000, you know. Sometimes you can get one that'll go longer. You know, foreign automobiles tend to run for a longer period of time. That's why I like buying foreign automobiles. You know, my mom is like, I can't believe you buy a foreign automobile. I'm like, well, Mom, you know, I'll be able to get 500,000 miles out of this automobile. That's like 5 American-made automobiles. And it's only going to cost me this much, whereas if I bought 5 American automobiles over the time frame, 5 times 7 is in the last 35 years. Basically, in 7 years, you put 100,000 miles on automobile. So in every 7 years, you buy a new automobile. It's what kind of most people do. 7 to 10. So let's say it's you get 10 years out of it. Well, you know, if you get 10 years out of it and you put 100,000 miles on it, you know, then you buy 5 of them in 50 years. Well, we want to at least live to be 50 years old. I have surpassed that. So you know, the amount of money you will spend on 5 American-made automobiles, 5 of them in that period of time, versus buying a Mercedes, is a heck of a lot more money. You tell me what's smarter. You know, I mean, I know what's smarter. I can put the numbers together. You know, I'm not buying these automobiles, Mercedes and whatever, because I want to look all cute riding down the street. It has nothing to do with that. You know, I buy stripped down Mercedes because I want the engine. You know, that's what I want. I want the engine. It's just plain white. You know, no frills on it. It's just the engine. It's going to run forever. You know. People are like, oh yeah, well he thinks he's. I'm like, you don't even understand what I'm about. You know what I'm trying to do. People jump to conclusions. Well, there's like, you know, and I get that all the time. It's like, oh, I saw you drive up in a Mercedes. I'm like, well, I've had it 7 years now. Already, runs like a dream. Still, and I bet I get many more. I'll probably drive that car till the day I die. They'll probably bury me in it, you know, except I'm going to be cremated. You know, and it cost $42,000. Well, that was 7 years ago. That was a lot of money 7 years ago. What, automobile today? You buy pickups that cost $58,000. $58,000. today, 7 years later. You know, I know what's smart. You know, I've been looking. I've been watching. You know, I understand how America works. Anyway, just food for thought. Just think about it a little bit. Okay, anyway, these are some things, exergonic interactions. Let's talk about exergonic because I love these reactions, and I'll tell you why. Exergonic reactions give off energy. Give off energy spontaneously. Spontaneously. All right. Without you having to do anything. And I have a little story. This is a little short story. And I know I don't have time to tell stories, and I love to tell stories, but okay. This one is very specific to exergonic reactions. When I was younger, last year, my parents gave me a chemistry set for Christmas. And so you know, they wouldn't let me work with it in the house, so I had to work with it in the garage. Well, it was Christmas. It was cold in the garage. And so I remember, you know, out there with the chemistry set on some thing my dad had built, the work table. Work table. You know, and I've got test tubes and I've got chemicals and I've got all this stuff, right? I feel like Mr. Scientist, and I had no clue what I was doing, none at all. So I kept doing all these mixing of chemicals, and of course, what I'm looking for is an explosion. You know, that's what I really want. Bless you. I want an explosion. What else would you want out of a chemistry set? What? Explosion. That's the best thing you can hope for, right? I mean, for me, that'd be like the best. Anyway, so I'm mixing all these things together. Anyway, at some point, I don't even know what these things were, but I put this cold chemical A into a test tube and mixed it with the cold chemical B, whatever those were. And I'm holding this test tube, and it begins to warm up, and I think I'm onto something. And then it begins to get warmer, and then it gets so freaking hot that I have to put it down. And I'm like, this puppy's going to blow. So I stand back, right? I get back because it's just going to blow up. I know it will, right? And I'm standing away from it. You know, I've got goggles on, you know, making me feel really, really scientific. Anyway, and it didn't blow up. But at least I knew I was onto something, you know, that at least I produced so much heat that I couldn't hold it, and I had to put it in a test tube rack. So the point is, I didn't get an explosion. The second point is, the other point is, I put cold chemical A and cold chemical B together, and it automatically started to warm and get hot. I didn't add any heat to it. I didn't do anything. I just stuck them together. And energy came out of it like crazy. There was a lot of heat that came out of it. That's an exergonic reaction. You know, if I can add two things together and energy comes out of it, that's pretty cool in my book. You know, and at the time I didn't understand what exergonic reactions were, but now I do, and I always tell that story because to me it is so applicable to exergonic reactions. Anyway, so those you know, you give off energy spontaneously. The other type of reaction is endergonic reaction. Means that if I want a reaction to occur, you have to add energy. Add energy for reaction to occur. Well, that's what we tend to think of. Reaction to occur. Yeah. So if I'm in chemistry down there with Miss Jackson, and I want some reaction to occur, then I put cold chemical A and cold chemical B together, and then she says, well, you have to put that over a Bunsen burner in order to get your reaction. So I have to add heat into it to get my reaction. So we tend to think mostly in terms of ender reactions that consume energy. You got to put energy into it to get a reaction. Not all. Sometimes energy just comes out. And what the cell does it has the ability to tie these two together. The reactions that give off energy can run the reactions that require it. Not bad, pretty smart. And that makes the cell work. So I have energy, I have reactions that spontaneously give off energy. I can use those to run the reactions that need energy. And then you've got a working system that continues to work all on its own. You don't have to continue to supply it with energy. You don't have to continue to pull up to a pump and add gasoline. You don't have to continue to shovel food in your mouth. You know, I mean, if it were just the one cell, but you would have to supply it with some form of starting material, at least some form of starting material. But you basically have a running system. You know, and plants do the best job of this of all, because all they need is some really simple things: carbon dioxide, water, and sunlight, really. Occasionally a few other things, but those are your basic components. CO2 out of the air, water typically out of the ground, sunlight, it's out there. Okay, those three things, and they can grow to be humongous, huge trees that survive for hundreds and hundreds and hundreds and hundreds and hundreds of years, which is amazing. And they're really just tying these two reactions together. So those are incredibly important, especially to a living system. You can't even talk about biology without getting into exergonic and endergonic reactions. So, yeah. Now, so what we're starting to get into is what's called metabolism, and that would be all the reactions that occur within, say, a cell. That's metabolism. All the reactions. Well, or you could extend that. All the reactions that occur within the entire organism, whether it's a dog or a cat or a guppy or we don't care, a rattlesnake or a spider. It's getting close to Halloween, my favorite day of the year. My favorite day of the year. Oh, man. I love that so much. People are like, I like Christmas. I'm like, no, I like Halloween. No, that's fun. I like to buy spooky things. You know, things that look horrible and disgusting, and put them out. For kids to go, oh, I don't think I'm going to that house. I won't. You go. I'm not going. It's the brave person that rings the doorbell, you know? Everybody else is hanging out, waiting to see what's going to happen. And then you open the door real slowly, just so you can like look out. It's like, what? What? What do you say? And of course, what they have to say before they get any candy or anything is trick or treat. That's all they had to say. But you know, usually they just go running off like, this is too weird. You know, I'm like, what? What? Tell me what? Kids are not ready. Oh man, it's so good I didn't have children. God knew what he was doing. Like, oh, he'll torture them to death. They'll run away. By age 6, get me out of here. This man is demented. What fun. Anyway, so a metabolic pathway, what we do is, you know, we will take molecule, we'll start with something like molecule A will be sugar. That's what we start with typically. And we convert it to molecule B, which converts to molecule C, which converts to molecule D, which converts to molecule, you know, and at the end of here somewhere, molecule, I don't know, X, we end up with a product. That's what we wanted. We wanted the product. Well, this whole set of reactions, that is your metabolic pathway. It took several steps to get there. And many times you have to have enzymes to make that work. So from A to B, you have to have enzyme 1. From B to C, you have to have enzyme 2. We got to have enzymes for these things to work. From C to D, yes, enzyme 3, and so forth. So you got many enzymes to make these metabolic pathways work. And that's what we're beginning to work with would be, okay, how are we going to produce energy? Well, it's not like you go, all right, you mix molecule A and molecule B and you get energy out of it. Well, that would be great. But, you know, it wouldn't be like so much to go, well, okay, so this is doing this and that's doing that and this is doing this other thing, you know, and then putting it all together to really get a comprehensive understanding of how that works. But that is how it works. And I didn't invent the system, and I always tell students, you know, if you don't like the system, complain to God. And it was his system. He developed it. You know, if you're like, I don't like that, well, tell him. He's listening anyway. But you might as well just tell him, God, you could have made this easier. But believe it or not, he made it so incredibly simple. He really did. You get right down to it, it is so incredibly simple. It is. It is, it is, it is. I promise you, it is so simple that it just knocks my head off. I'm just like, really? This energy coupling, that's what we were talking about. You're tying a reaction that gives off energy, which is exergonic reaction. So this is an exergonic. Spontaneously gives off energy. And you're tying it and making the energy that you get out of that run a reaction that needs the energy, and that is an endergonic reaction. All right. Beautiful system. Very nice. We have those that give off energy, exergonic, those that consume it, which are endergonic, and of course we then can run the cell. Pretty sweet. Very sweet deal. I like it. I like it. People are like, you like weird stuff. Well, maybe so. But I'm not the only one. Like, you know, things that may be a little different. Things that, you know, and it's just your curiosity. You know, some people are not curious about some of this stuff, and some people just are. How does that work? You know, I've always wanted to know. But not about like an automobile. I don't care how an automobile engine works. I do understand that for a good deal of it. But I don't really care, the combustion engine. You know, not really all that fascinated by that, where I'd actually pull an engine apart and then put it back together and rebuild an engine and put in a manifold, whatever that is. You know, I don't even know. No. I know where the gasoline goes and the oil, and I can change a tire. Yeah. But a lot of stuff, I don't care how it works. But man, when it comes to living things, I'm just like, okay, gotta figure this one out. And there's so much cool stuff on YouTube. Normally, I would have enough time to show you people the really cool stuff on YouTube. I may just start sending links so you can watch this stuff at your leisure. It's like there's some of that stuff is like you would not believe. Real life is so much more fascinating. I can promise you. I swear to you, is so much more fascinating than anything you can see on the screen. You know, I mean, I watch the Marvel movies because my brother's boyfriend is like a producer for Marvel Studio. I mean, this is big time. It's a pretty big time. He's a producer. Okay, so I make it a point to go see all those movies. Now, so if we're ever discussing, you know, whatever, Captain America or whatever it is, then I'll be able to participate in the conversation. But, you know, I look at that, and I just want to send him, you know, the links to the YouTubes on some of these things because they're just absolutely hysterical. I've been watching some of them lately, and I just laugh and laugh and laugh and laugh. And they're so much more fascinating and so much more interesting than what they can do with the special effects and all that mess on the screen. It's like that's just a bunch of hooey, that's a bunch of crap. To me, it's just crap, just crap, just crap. Show me the real life and have somebody who can narrate that who has a really good sense of humor. Oh, I'm in. I'm totally in on that. You know, love it, love it. Anyway, so yeah, no, I'll go watch movies, but do I find them interesting? Usually not at all. You know, I like a good love story. That's kind of real, kind of real. You know what I'm saying? I mean, really, I like a good love story. I'll cry. I'll cry like a little girl. And they get back together, you know, it's all happy and that's silly. That's silly. Anyway, okay. So what we're going to do, and this is the way your cells really operate. This is what we have to make, ATP, adenosine triphosphate. And so what it really consists of, it consists of a ribose sugar. Now, if it ends in an OSC, you know it's a sugar. So ribose, that's a sugar. Plus, it attaches to an adenine. Somebody's talking, which means you're disturbing whoever's around you. I don't really care if you strip off butt-ass naked and go run around the room. I've made myself clear about that. So anyone wanting to do that, feel free. At any point in time, just strip it off and go around the room screaming your head off. Will not bother me at all. But if you disturb other people, which that would disturb other people, I'm sure, I would have to say, no, I didn't tell you to do that. I'm just saying, you know, if you feel the need, then go for it. But you know, yeah, I got to protect the other people in the classroom. That's part of the job. It's part of the job description. Anyway. So ribose sugar, adenine is one of those nitrogen bases. You know, like in DNA, an adenine will pair with a thymine. You always get base pairing. It's double-stranded. Adenine pairs with thymine, and cytosine pairs with guanine. You got two strands of DNA, and it goes into a helix. So you got your nitrogen bases paired in the middle of the helix. So adenine is one of the nitrogen bases. Anyway, you've got a sugar and a base, nitrogen base. And then you've got these three phosphate groups, so three PO4s is what they are. So that's one phosphorus of 4 oxygen. The next one I'll just put PI instead of put PO4, and the next one I'll put PI instead of PO4. All of these are PO4s. The I means inorganic phosphate. It doesn't have carbon. It's not a carbon-based thing, so it is inorganic. So that's what ATP actually is. Well, this thing right here is the adenine, what they call adenosine. Okay, and then I have triphosphate, 3 phosphates, 1, 2, 3, 3 of them. Adenosine triphosphate. Okay, now notice how many oxygens you got here. Right here, 1, 2, 3, 4. That means you're electrons that direction. Electrons are going this direction. What's that oxygen? Oxygens are electronegative. If you're not sick of hearing that by now, you should be. They're electronegative. They tend to pull electrons closer to them. Okay, but this one will also have 4 oxygens. So the electrons are going to be pulling this direction as well. And this one has 4 oxygens. The electrons are going to be pulling this way as well. Okay, so what you end up getting here is really a very strong negative charge here, a less strong negative charge here, and even a less strong negative charge here. So the strongest negative charge you have. So negative to negative, or let's just say North Pole to North Pole on a magnet, they don't want to hang out. They tend to push away from one another. So it doesn't take much energy to get this bond to break right there between the second and the third phosphates. And if I can get it to break, this third phosphate will just shoot off. It will just move away very, very quickly from the second phosphate. So that's kinetic energy. It is the movement of that third phosphate, the movement, which is hard to wrap my head around. I don't know. You may just go, I got it. I'm not that person. I'm like, huh? The movement of this third phosphate away from those other two phosphates, this pops off and goes way over here. The movement is how energy is released. This is how we run everything in the body. It's really how we do it. By pulling that third phosphate off, and it doesn't just like drop off. It goes, ploing. It fires off of there. Negative to negative, they don't like it. But this one, third one, is so strongly negative, it just goes, moves very quickly. I like sound effects. Moves very quickly. Okay, so it is the movement that provides the energy. It is the kinetic energy, the movement of it. And that provides the energy to do cell work. And that is something that I just go, my head doesn't grasp that. I'm not quite wrapped around it. But I do understand that energy occurs when there is motion. And it's been defined. It's been told to me over and over and over. So I have to go, okay, there's energy of motion. We call it kinetic energy. So anyway, so that is actually the energy that runs cell right there. That's our energy. The power, everything we need to do, to think, to run, to walk, to drive automobiles, to whatever it is you do. Okay, what we're left with, once I pull that third phosphate off, is an ADP with adenosine diphosphate instead of triphosphate. You're only left with two phosphates, this one and this one. And that third phosphate was pulled off. So you've lost your third phosphate, but you've also released a lot of energy. All right. That's the point in doing this, to pull off that third phosphate. So we get energy by taking the third phosphate off. Well, if we want to go the other direction, if I want to make ATP, so here's ATP breaking down, but if I want to make ATP from these same pieces to generate ATP, this means I have to put energy in order to take my arrow to the left. So in order for the PI, the third phosphate, to add to the second phosphate, that means I'm adding a negative charge particle to another negative charge particle. You better add energy in there to do it. So I have to add energy in. If my arrow is going to the left, energy has to go into it. Well, that energy comes from exergonic reactions. This is from exergonic reactions. You know, and so this is the point at which it starts to get a little bit fuzzy for a lot of people. It's like, you know, I was with you till now. I understood the cell, and you had the Golgi did this, and the ER did that, and the nucleus did this, and blah, blah. But now you're talking about some pretty bizarre, wild, crazy stuff. And it kind of is, and I kind of understand that people would go, what are you talking about? But if you lose the third phosphate, if you pull it off, it's going to fire off of there. It's negative to negative. They don't want to hang out, so it fires off. That's kinetic energy. That powers how we produce energy, which is how we make ATP. So if I can get it to break down to ADP and PI, release energy, but I can use that energy and to do something else. But typically, where I use energy to go to the left to make ATP, I'm going to get most all of that energy from exergonic reactions. You wouldn't get it from the energy released by breaking down ATP, because that would be pretty stupid. You would be getting energy out by breaking the phosphate off, and then you'd be using that energy to put the phosphate back on. You wouldn't accomplish anything. You pull the phosphate off, you'd get energy, you'd use that energy to put the phosphate back on. What have you done? Just a whole bunch of taking phosphates off and putting them back on. That accomplishes nothing. So the energy used to actually make this go to the left, this direction, to put a phosphate back on, the energy we use is actually from exergonic reactions. So that provides the energy to put that phosphate onto this, not the energy that came out of it. This energy is used to do cell work, so that becomes cell work. All right, so it is kind of an interesting topic, and I do love the energy discussion totally when it comes to the cell. Pardon? Cell work is anything the cell needs to do. If it needs to add an amino acid to an amino acid, if you need to break a sugar down, if you need to have a muscle contract, if you need to think, neurons have to pass basically electrochemical energy from one point to another point. That takes energy to make that work. That's how your brain works. It allows for cellular work. It allows your body to work. The energy, that provides the energy that we need in order for the body to function, to keep it alive, for all of the cells to work, for cell work. That'd be all 70 trillion of them to work. But the energy used to actually make the ATP, that comes mostly, or not mostly, but some of it comes from exergonic reactions. And we'll get into this a little bit more in more detail. We're only about probably less than 10 slides away from finishing this. And then on chapter 6, that chapter will, I can probably do that in 2 days. So I should be able to finish this, hopefully, I'm thinking by Monday. And Module 2 closes on Monday at Monday night at 11:59. But I think I'm finally getting into how much time I need to take for each module, which is, we didn't know. I didn't know what it would take to do that. So I know you've kind of had to go, well, he's extending the module again, you know. It's hard for me to know how much time it takes given this time frame that I have to work with now. So it is interesting. But we will survive. We will persevere. We will win. We will win. Okay. Have a good day. Have a great day.